So thank you for having me. It's just really a great pleasure, and I hope to visit you in person. So this talk is based on a relatively recent magazine paper that I wrote with two of my former students, Raksha Ramakrishna and Hoito Wai. Raksha is doing a postdoc at KTH, and Hoito Wai is now a faculty at Chinese University of Hong Kong. And the title of my talk essentially clarifies what's the content. It's a user guide to low-pass graph signal processing and its application. So I'm deeply interested. This is something that has interested me for a while, since my more communication-focused days in network processes. And initially, my interest was in algorithms that work over networks. In fact, we wrote several algorithms on gossiping and distributed optimization, and I still am interested in this field. But as I was studying these processes, I became increasingly interested also in network processes that occur on networks and that produce data that therefore are indexed by this network. And graph signal processing has been emerging as a tool which is very useful to analyze this type of signals. By the way, graph signal processing is also used in other applications which analyze the graphs themselves for embeddings. But I'm going to focus on signals that are, again, indexed by graphs. And here I have a few examples. It could be processes that occur because of relations among different agents. This happens in social, economic, knowledge networks that include documents and data, and biological networks, and also in network infrastructure where the network is sort of explicitly known, like the grid, gas infrastructure, pipelines, and so on. And so the agenda for this talk is I first want to define what is a smooth graph signal, smooth by meaning low pass. And I want to also explain some applications and sort of justify why one should focus on this class of graph signals instead of looking at graph signal processing in general, which I'm not advocating. I'm just simply saying this is an interesting case. And the reason also why it is an interesting case is that there are certain properties of smooth graph signals that lead to specific tools for processing these data. And so it's interesting to study them because they are applicable to real signals and they have special properties that facilitate some analysis. I'm going to start with a premise on what is graph signal processing. And I'm sorry if you are terribly familiar with this subject. I want to have a talk which is self-contained. And then I will talk about what I mean by a low-pass signal. And I do so by introducing what is a low-pass generative model for graph data. So I will both introduce the definition and then some applications. And then I will go on with my user guide and wrap up the talk with some conclusions. So what are the basic notions of graph signal processing? First of all, let me tell you that the interest in graphs for data analysis has been dominating machine learning and signal processing for many years, starting from. So this was a pretty picture for my introduction about graph signals and all the different situations where they arise. This is the agenda of my talk, as I said. What is a smooth graph signal? Where does the behavior occur in real signals? And how smoothness enables some analysis. And so I was starting with my premise on what is GSP, and I started acknowledging that graphs are ubiquitous in data analysis these days, starting from Bayesian networks, where we are looking at joint experiments and trying to model the relationship of conditional independence among random variables to facilitate statistical inference. But in this case, there are no nodal signals. There are sort of joint distributions that are conditional distributions that are encoded in the graph. There is also widespread use in machine learning of random geometric graph, trying to capture the topology of data in high-dimensional spaces. And one of the very useful tools for unsupervised learning is clustering these networks. Signal processing is slightly different because, as I said, is based on the generalization of DSP and filtering operations on signals that are indexed by graphs. And so let me talk about the modeling. So the idea is that you have vector in n-dimensional space, and you are indexing these vectors through the nodes of a graph. The graph is going to be denoted by G, which has a set of indexes of vertices, which is V, and a set of edges E. And A is the weighted adjacency matrix of the graph. And the idea behind GSP is essentially extending the notion of what is called the shift operator, so the Z variable of the Z transport to a -1, through an operator, which I call L, which is a function of the adjacency matrix. So this is a local operator in the sense that we'll try to preserve the sparsity of the matrix A. And so this is has been, after one essentially has identified good candidates for the graph shift operator, it has become apparent that a lot of the functions that are performed in GSP can be generalized. And really the birthplace of GSP was a paper by Puskel and Mura in 2003, where he tried to have exactly this algebraic interpretation of digital signal processing by focusing on the adjacency matrix of a directed cycle graph, which I'm showing here on the left. And so this cyclic graph has an adjacency matrix that everybody can see is a circulant matrix. And the idea was to trying to interpret filters as matrix operators, essentially. So L, as we said, is not necessarily A, is a function of A. And the idea was, what is a filter? A filter that is, it's a linear operator. A linear time invariant filter is a linear operator that is invariant with respect to the shift. So if we call now abstractly geometrically an algebra, the shift as this operator L, what has to happen is if I have an input-output relationship, X equals this filter times S, this is the filter operator, then if I multiply X by L, I'm shifting it. And the idea that this should be identical to what happens if I shift the input implies essentially that this operator has to commute with the shift operator L, right? So multiplying L on the left by the graph filter should be equivalent to multiplying L on the right side with the graph filter. Now, that is possible if and only if the operator H of L is in fact a matrix polynomial, and it doesn't have to be of finite order, it can be of infinite order. And so what graph or network data are, if in a generative model that is based on these graph filters, is essentially the output of some matrix polynomial. That's what essentially the gist of the idea is. And so when we look at this, we can look at S, the input, as an excitation, and X at the output. Now, is there a real input and a real output? No, you have to interpret this as we interpret the modeling of stochastic processes through an excitation and an ARMA filter that shapes their spectrum. So really, this is trying to capture properties, second-order properties of the signal, and possibly, if the analysis confirms that this model is true, you can essentially derive all the statistics. This generative model is true, you can derive all the statistics. So, as I said, this can be of infinite order. So examples could be identity minus alpha, the shift operator, to the -1. So this would be the equivalent, since L, you can compare it with the shift operator. This would be equivalent of an AR1 filter, an autoregressive model of order 1, or it could be a matrix exponential. These are all valid graph filters. And initially, the idea of generalizing to an arbitrary graph was to utilize the adjacency matrix because of the inspiration drawn from the cycle, the cycle graph that is directed. So in that case, it will be a proper shift, but soon enough, people kind of stayed away from that, and they instead utilize the Laplacian operator, even though there are other generalizations which are particularly useful when you have undirected graphs. This Laplacian operator has prevailed. And so what you can imagine that the Laplacian is not exactly only moving things around, but it effectively has more of the nature of the variable S of the Laplace transform. So it's a differentiator as opposed to the shift. Speaking about differentiator, so what is the equivalent of a derivative on a graph? It's something that takes the data from adjacent point and calculates the difference. And this operator is in fact the incidence matrix. And so the incidence matrix here, I define it as a matrix which has a dimension equal to the cardinality of the number of edges. So the number of edges times the number of nodes. Some people define it the other way around. So the transpose of that. But in any case, so if E is the index of the edge and V is the index of the node, we have -1 if the edge E leaves the vertex V, and +1 if the edge E enters in the vertex V. And so this is the oriented Laplacian, which is also defined for undirected graph, because it's like saying the derivative, you can stipulate what is the sign of your derivative. And oftentimes what we are interested in is, in fact, the magnitude of that derivative itself. So obviously this vector D times X contains all the differences of the values of the nodes that are adjacent. And in fact, if you have a constant graph signal here proportional to 1, you always are going to get 0 derivative, as you would expect. But now the dimension of this derivative is equal to the number of edges, right? So now you don't have, like you have for a signal in time, for a digital or for time series, a finite difference, which you can associate or shift to another node, right? Because it doesn't have in general the same dimension. So in the cycle graph, you have a number of edges which is equal to the number of nodes. But in general, the number of edges for a strongly connected graph, which is not a tree, is going to be greater than the number of nodes. And by the way, you can have a weighted graph. As we said, we had this weighted adjacency matrix. In this case, you will take the weighted difference between the two signals corresponding to connected edges. So how do we operate with graph signals with a generative model that depends on this graph shift operator that though creates a mapping through this graph filter, which is 1-to-1. So you have an excitation which has the same size of the nodes, right? Is equal in size as the number of nodes, and so the output also has to be the same size, right? So instead of utilizing the differentiator D, what we utilize is the so-called Laplacian operator. And if we can compare D with the gradient, basically the Laplacian operator will be the equivalent of a Laplacian for continuous fields. And so for a weighted graph, another way of writing the Laplacian is by essentially expressing it as a function of the incidence matrix, as I'm showing here. Now, obviously, since D times 1 is 0, then obviously the Laplacian is always a 1 eigenvector, which is 0. And I'm not going to delve too much into spectral graph theory, but the nullity of the Laplacian, there is a very famous result in spectral graph theory that says that the nullity, the number of 0 eigenvectors of the Laplacian, is identical to the number of connected components of the regression. So if that's the only eigenvector, essentially we have a strongly connected graph that has a path between every two nodes. So what would be, so if we use the Laplacian with the factor gamma between 0 and 1, then iterating with the Laplacian is essentially going to keep making derivatives and so smoothen the signal, right? So a graph that is subject to repeatedly to the Laplacian essentially is smoothened because you are taking over and over derivatives. Now, if we have something which is indexed on an irregular support, then the next question is, what is the notion of frequency? What does it mean to have high frequencies versus low frequency? And so we need to express a notion of variation in the adjacent entries. What we know is that for a time series or for a continuous time signal, A high frequency will mean high variations in contiguous points in time, and for a low frequency would be exactly the opposite. So the metric that can measure variation is, in fact, could be essentially the Frobenius norm of the graph derivative. And this Frobenius norm for the graph derivative will be exactly equal to the quadratic form that is defined here, where the Laplacian is in the middle. Okay, so this, yes.
Sorry, can I ask a question?
Of course.
So I was just thinking, like if the beginning that the analogy that you drew with or you talked about what Jose's work did in terms of like connecting it to the cyclic graph, right? So in there we use the adjacency matrix. Is there like, if we think of in a traditional signal processing sense, is there an equivalent operation that we do with the Laplacian for that cyclic graph, or that you can
could
think
rewrite essentially? So the idea is that you could rewrite difference equations, particularly if you're looking at second order properties, in terms of the finite differences, right?
Sure.
What the Laplacian will do, it will take the central value and take the finite difference with respect to the two neighbors, right? As opposed to taking just the difference between the two. That wouldn't work, right? Because again, for an arbitrary graph, you have more edges than nodes, so you don't know how to do the association. So what I say usually is that you should compare it with the finite difference, or think in terms of the S differentiator in Laplace transform. That's really what more similar to L. But since you are symmetric, it does create some problems if you want to map one-to-one. So it's better when you're looking at second order property, which is a spectrum in a way of the graph. Signal covariance is good at expressing. So in those cases, you will be always fine.
Sure. Thank you.
Okay. All right. So again, so with this idea, right? So signals have small variation, right? They have a small value for S2 of X should be the low frequencies, right? Then we have essentially a mapping between what we consider a smooth signal of a graph and the frequency itself. In fact, the smoothest signal of all will be one that gives me zero variation. And we already know that there is a null vector, right? If we interpret these as, if we normalize this variation by the norm of the vector, we have exactly the Rayleigh quotient with the Laplacian matrix, right? And so the smallest eigenvector will be the smoothest signal, which is in fact the all one vector, which is perfectly reasonable. And the frequency will be in that case equal to the eigenvalue, which is zero. And we can understand that then we have a ranking as long as the eigenvalues are different, then we can consider each of the eigenvalues order in increasing order, as the frequencies. So the second smallest is the second lowest frequency, and so on and so forth, right? So as the eigenvalues increase, the frequency increases because this variation increases. Now, is that consistent with DSP? It is, right? So if you, instead of taking the adjacency matrix is circulant, so the eigenvectors of the adjacency matrix, in fact, are the same eigenvector as those of the Laplacian matrix. But since I obsessively talked about Laplacian, I just want to mention what are the eigenvectors of the Laplacian. They are identical, but the eigenvalues for me are a little bit more important. They are these positive numbers, and the eigenvectors of a circulant matrix are the complex exponentials of the DFT.
I have a question.
Yes.
So I guess you sort of said, of course, all the eigenvalues have to be different to have an ordering. But is there what does it mean when you have the subspace uncertainty? That doesn't seem to have even a corresponding idea. If you have a repeated eigenvalue, that, I don't even know. I don't know. I'm trying to figure out what that even means.
Yeah, so the repeated eigenvalues, for instance, you could have disconnected components, right? So that would create multiple zero frequencies.
Right. Okay.
So in that case, that's kind of an extreme case, but you would want to look at the signals separately, right? It doesn't really make sense to look at them in a combined fashion, because they don't interact, right? You
At all,
can't
right.
take a generative model that says I interact with this, because they don't, they don't transfer one in another. So even though in general you could have repeated eigenvalue, when you have connectivity which is somewhat randomized, it's very difficult.
Yeah, it has to measure zero, right?
Right.
Yeah.
But they can be close, and this is kind of a one annoying difference of having nice frequencies like this one, right? Graph frequencies are this one, which are the frequencies essentially that we use, the one-to-one with the frequencies that we use in the GFT versus the other case. In fact, these exactly tend to eventually, for n very large, to be 2k, k over n tends to be the frequency. So it's exactly the one that we use. In other cases, all I can tell you is that this kind of large randomized matrices tend to have distinct eigenvalues.
But does it mean anything for them to be clustered, like the
clustered? Yes,
clustered
and that's
stuff?
because the matrices typically that can be clustered tend to have kind of eigenvalues that go in steps.
Mm-hmm.
And so even though what I said is not the extreme case that they are disconnected isn't true, it is also true that there is kind of small influence between the different components.
And so that's kind of like having multiple disjoint frequency bands.
Yeah, exactly. Kind of having multiple processes that occur in different parts.
Cool. Thank you.
Of the system. Thank you for the question. Actually, I like these interactions. Okay, so then let's see if this is a good idea of defining variation like this. So here I'm looking at the magnitude of the eigenvectors for the Laplacian of this little graph. You can see that this is a graph that tends to have two communities, right? So the all one vector obviously corresponds to lambda equal to 0, and it's constant because it's 1. But you can see that as I grow in frequency, the second tend to clearly highlight, has a variation that depends on the, sorry, this is not the magnitude, this is actually the signed value. This variation depends on the cluster. So it's smooth in each cluster, but varies in the two, right? So this is 0, 0.5 and minus 0.5 is the scale. And as I increase the order, right, so there are 15 nodes here, you can see that there are more variations even in this graph. So, and in fact, one of the highest eigenvectors are used also in concepts of centrality. So they're actually singling out important nodes in the network. So they tend to be actually sparse as long as the network is relatively sparse. So let me now define the graph Fourier transform, because if I have a spectrum, and if I talk about spectrum, I have to talk about Fourier transform. Okay, so what is the Fourier transform? So for the discrete Fourier transform, the basis of the cyclic graph are exactly the eigenvectors of the graph shift operator. And so this kind of straightforwardly leads to the consideration of the eigenvectors of the Laplacian, which is the shift operator for an arbitrary graph, as the basis, the Fourier basis for a graph signal. And so the GFT here, I will denote it by x tilde, is simply obtained by applying u to the minus 1 to x, which is the graph signal itself. And obviously you have an equivalent transfer function for the graph signal. And this transfer function is nothing but a diagonal matrix which has as diagonal elements these polynomials. Lambda, I remember, are the different frequencies. And these are the weights of the matrix polynomial that define the graph filter operator. And why is this a reasonable choice? Because if I am taking, if I want to write the relationship between the graph signal Fourier transform at the output of a graph filter with respect to the one at the input of the graph filter, what I have is the well-known relationship that I have also in DSP, which says that the DFT of the output is equal to the transfer function coefficient multiplied by the DFT of the input. And so I have exactly this here. This is the diagonal matrix, entry by entry. I multiply the input Fourier transform by those coefficients, and I get the output. And again, the convention is that lambda 1 is 0, and all of the other frequencies are, in general, less or equal, but typically they are all distinct. So what are we interested when we do analysis? Typically, we are interested in the analysis of multiple observation to identify sort of the structure of the signal. And oftentimes, the exact matrix L is not known, or it's simply something we want to derive through modeling. So unlike the case of time series analysis, where we are trying to derive the coefficients of this generative model, and we know the graph because it's simply the cyclic graph, in this case, we have an extra unknown potentially, particularly in networks that are not infrastructures, right? They're biological network or financial networks. Like we don't know necessarily the ties between these agents. So, so we're going to utilize the notation that now there is an index T. T doesn't have to be time. This could be just simply multiple observation. And oftentimes we will be interested in second order characteristics of X. And so in this case, actually, as I said, the symmetric Laplacian is pretty good for modeling. Now, so the regime in which we are is when we are assuming that these data X tilde X of T are such their Fourier transform tends to be sparse. And so in a generative model, typically you ascribe these peculiar properties to the filter that filters the input excitation, which typically is assumed to be broadband, so to speak, so not sparse in the GFT domain. And so that means that then the transfer function of the graph filter should be sparse. And now the immediate consequence that happens is that even if you may have a very high dimensional graph and therefore a high dimensional set of observations out of this graph signal, but if the H is sparse, all of the graph signals that are observed are sparse also in the GFT domain. That means that you can select, so let's say that F is the subset of these graph frequencies where the transfer function coefficients are significant. So you could select those columns of the GFT and say that essentially X can be expressed as a subset of coefficients X tilde that are the high graph frequencies that correspond to the support of H times this tall matrix that contains only the columns where the spectrum is significant. So it's a low rank. So this is an immediate observation that these kind of signals are amenable to the simplest form of dimensionality reduction, which is projecting them on a subspace essentially. Now, oftentimes these observations are not completely independent observations. They are a time series of observation. And so there is also a relationship in time that we want to represent. So we could actually do away completely and forget about time just by utilizing a graph that is the composite between the spatial graph that models a spatial phenomenon and temporal graph, which again will be the cycle graph. And in fact, it can be shown that a graph temporal signal, like the one that I have here, can be expressed as a graph signal on the Cartesian product graph. And it's known that for the Cartesian product graph of these two graphs, the Laplacian is going to be given by this relationship where this symbol here is the Kronecker product. So you have identity Kronecker, the Laplacian for the spatial component with this graph, and then this is simply the circular Laplacian I was showing before for the cycle graph Kronecker identity. So this is kind of block circulant. And for this operator, not surprisingly, the GFT is simply the Kronecker product of the respective GFTs for both Laplacians. But oftentimes it's actually convenient to write the equations writing, in fact, convolution Z transform for the things that occur in time and relating them with what happens with this graph matrix polynomial. So we can write a graph temporal response instead of putting everything in this big Cartesian product operator L. And so in this case, L is simply, I am omitting the index here, Ni. I mean that's sort of the spatial Laplacian. And then the graph filter has this form where every power of P that corresponds to the matrix polynomial has a different coefficient in time. And oftentimes in the analysis, people use a separable filter so that HPT is in fact the product of two filters But in general, if you're trying to model with a generative model, that's not general enough. And in fact, most cases that I've encountered in terms of modeling network dynamic, you cannot make that assumption. The assumption is invalid. So therefore, what will be the input-output relationship will be this spatial temporal convolution with this operator. And if you take the Z transform of this time sequence, you can, and then you take the GFT of that, then you can write an input-output operation, which is like this, where, again, this is an element-by-element multiplication. I could have written diagonal of this, and it's defined for every value of Z. Or corresponding, if you want to replace Z with e to the j omega, this will be the graph temporal GFT. Okay, and then all the properties of this operator essentially can be derived from this function, bidimensional function, which is a function of the graph frequency and of the Z variable. And a particular class that is oftentimes used to model input-output relationship is the generalization essentially of the autoregressive moving average model, where you have this recursive equation, and therefore you have this relationship in time and frequency. So let me now go to low-pass signals. How am I doing time? Not too bad. So now we know that for a linear time invariant filter, you can have low-pass, high bandpass, high-pass, or filter with sparse supports, right? So, and we said that if you have in general a sparse support, which either of these cases could represent, then you have a low dimensional space. But what's interesting about low-pass graph signals is that you are picking in this low dimensional space the components of the GFT that correspond to the lowest frequency, which are the least significant eigenvalues of the Laplacian. And so, as we will see, this actually has a direct relationship with what is the structure of the graph, and particularly the community structure of the graph, and has a whole bunch of other properties, because what we are saying is essentially that the signal we expect tends to be smooth spatially, right? So smooth across communities. So this has nice properties. It's something that also empirically is definitely visible in signals that belong to this class. So they're also useful because they're common in practice, right? In addition to the sort of being tied to the community structure of the network. Now, what do we mean by low pass? We do not want to apply the strict definition of low pass filter, right? That it has a cutoff frequency and then the spectrum is zero afterwards. We want to have sort of a cutoff frequency which separates the dominant component from spectral components that are lower. So we are going to define a low-pass graph signal based on this particular ratio, eta k, that compares the maximum of the amplitudes of the, sorry, this should be H tilde, of the graph Fourier spectrum of the filter from frequency k to frequency n. So these are the high frequencies. Relative to the minimum of the ones that go from 1, which would be the 0 frequency, up to k, right? So for every k, right, you're looking at the ratio between the maximum of the ones that are at the high frequencies versus the minimum of the ones that are at the low frequencies. And so if this ratio is between 0 and 1, then essentially the lower frequencies are dominating, right? The spectrum of the lower frequencies is dominant. And so you will observe also the properties, these properties in the graph signal that you have modeled this in this fashion. And so k, the cutoff frequency k is the one for which eta k now falls to, it becomes less than 1, and we call it the bandwidth, okay? And as I'm repeating myself here, for a finite impulse response, oftentimes this condition that you have a cutoff or sort of an elbow in the spectrum of the Laplacian corresponds to some topological characteristics. Of course, you know, there could be dynamics that impose that, But if you're not taking something of very high order as a filter, if you have a strongly connected Erdos-Renyi type of graph, which tends to have a giant component, so you are in a regime where you tend to have a giant component, then you have very close by values for all of the eigenvalues, right? They're distinct, but they tend to be close as n goes to infinity. Instead, a graph that tends to favor these low-pass properties is often a graph for small orders of the filter is oftentimes something that has a block stochastic structure. So you essentially have some nodes that have like greater probability of being connected, and then there are some nodes in groups that have lower probability of being connected. So this gives some kind of, yes?
I have another question. But I shouldn't think about the fact that there are 5 communities here in this block model. It's not like the lambdas are grouped into 5 bands or anything like that, right? Because it's not, because each eigenvalue, the eigenvector covers the whole graph.
No, so in fact, the only reason why this tends to go in block is because there is this, the algebraic connectivity tends to be low and tends to be close to have a number of zeros that are equal to this. So what it does it abruptly. And the eigenvalues are the eigenvalues of this group of components, right? And so each of these components has 1 0 eigenvalue in isolation, right? So those guys tend to be the ones that go down, but then the other eigenvalues are pretty large. So if you organize them, you see this elbow, right? And then this little group that is that are all low.
When you have I mean, I guess the thing is, this is not this type of graph, but if you have things like preferential attachment models or these other sort of graphs with like heavy tail degree distributions, does that correspond to something in the spectrum or no?
It does. All the spectra are different because you have a different kind of sample of a random matrix, right? All I'm saying is that these elbows tend to be for things that have this kind of block
structure. Okay.
And the preferential attachment model doesn't really have that. It's just kind of big stars.
Right. Well, that's why I was wondering if, like, if I had, my favorite random network model, if I would be able to tell what the spectrum, this spectrum is going to look like.
Because you have a polynomial like in the eigenvalues, right?
Right.
So you can understand from these trends what you're going to observe.
Cool. Thank you.
Okay, so now I want to make some examples. Obviously, this is not comprehensive, and this is not really fair. I'm observing just the covariance of this type of signals and showing to you that these, the eigenvalues of the covariance decay, right? I'll show you that the eigenvalues of the covariance obviously are connected to the graph filter structure, right? And when you have the generative model, essentially this is one-to-one, right? If the excitation that you are assuming is roughly white, right, is just uniform everywhere and doesn't and independent, then this is exactly equivalent to the profile of the frequency. This will kind of affect the profile of the frequency response because, as we said, the frequency response are going to be polynomials of these decreasing eigenvalues. So some of them will be very small for the high frequencies, some that were because this is decaying, and some of them will be very high. Of course, you can choose the coefficients of this matrix polynomial so that you zero out exactly the high one. But as we will see in the models that we consider, that's not the case. And that's why even if you just look at the eigenvalues, this is related to what I was discussing with Anand before. What happens is as long as you have coefficients that don't try to zero out exactly the values, which are the high eigenvalues, what will happen is that you have, in general, a low-pass class filter. And the other thing that this highlights is that these signals these covariances tend to be low rank, which is a property that we found in general if something is sparse in the graph frequency domain. So what are these examples? These are the states, the voltage phasors, so-called, like the envelope essentially of the voltage over each of the different nodes, which are called buses of a power grid. These are this is again eigenvalues of the covariance of the stock values for a financial network. And this is a social network in particular is the Senate roll call, which I think is from 2014 to 2016, I don't remember. Okay, so does this make sense? Can we utilize this model? Well, this is where I say it's true in application. Of course, I don't know, I cannot claim that the roll call of voting on average looks like a graph signal that belongs to my generative model. But what I can claim is that in the literature on social science about opinion dynamics, one of the very common models utilized to capture how opinions are shared among agents is in fact a special case of a generative model, which is a graph AR1 filter. And basically what this is saying is that I am essentially on average, it's like as if I'm choosing a random one of my neighbors. If it is a weighted graph, I choose more often the ones that I weight the most. And if you take the expectation of how the opinion transfers from the other nodes to my node, you can actually write it in this form, where I have essentially exactly the dynamics which are defined by this equation. So what is this 1 minus beta? So this for beta equal to 0, right? So this will be a closed system where the opinions are just kind of spread around without any influence, external influence. So this beta is added to capture the external influence of some excitation, which is kind of private information that reaches these nodes. And that has nothing to do with the sharing of opinions among the nodes. So that's where this the Groot model arises and comes from looking at the limit for the case. The Groot literally goes for the regime for beta equals to 0, but a simple generalization of the Groot says there are some influential external nodes or simply private information, which is encapsulated by this excitation, that also contributes to the opinion of each individual node. So for a political situation, it could be that, of course, senators or congressmen and women are talking to each other. They trust some of their peers more than others. But of course, there are lobbyists and special interests that try to influence them in their decision. And also, you know, their constituents, obviously, hopefully. So in the limit as t goes to infinity, right, if you keep repeating these dynamics, you actually can write something which no longer depends on t, and you can consider a pure time graph signal without a spatio-temporal component. So in a way, when you just look at spatial phenomena, you're kind of looking at potentially the steady state solution of these equations. And then you have here this object, which is in fact a graph filter of the nature that I mentioned before, and where this alpha tilde is simply a function of these two parameters. And so is this a low-pass graph signal? We look at eta k. Eta k can be written in this fashion. It's not difficult algebra because of the eigenvalues of this matrix are 1 plus the eigenvalues of the matrix L times alpha tilde, 1 over that. And so basically, if alpha tilde is much less than 1, so I will have a low-pass graph filter, which means that I am not particularly very strongly influenced by other people. I oftentimes stick to myself and also listen a lot to these sources, right? Now let's look at finance data. In this case, what is most appropriate is actually to utilize a graph polynomial, not just simply a first order AR filter. And what one can look again is the equilibrium of this system. This is again a GFR-AR1 type of relationship. And in this case, though, I have, some of the sources of my excitation may be low rank. So some of the private information is limited, but it spreads across different groups of the network. And so the sparsity of B are the neighbors that are integrating these sources of information and elaborating an opinion about what to do, okay? Or essentially, this could be instead, if this is the stock value, it could be the investments or the trust that hedge funds are putting in those type of investments, right? So the investors are limited, but the firms are many. And so in that sense, this excitation can be considered a low rank excitation. So you reach a condition of this kind. And in this case, the low pass ratio can also be expressed as a function of these filter parameters, this transfer function of these filter parameters. Again, I forgot the tilde here, this should be tilde. And so basically what is required to have a low pass graph filter is that H tilde is a low pass graph filter. In fact, in that case, the minimum of the low pass graph frequency component, spectral component of H are going to be dominating over the high frequencies. So this will be greater than 1 just as a result of HL being low pass. In power systems data, I'm not going to bore you with this, but too much. But basically what you have is a matrix that you can partition in what are the nodes that correspond to generators and what are the nodes that correspond to buses. And the GSO can be derived essentially from Ohm's law. Ohm's law says that the current is equal to the voltage times the admittance matrix. And this is the admittance matrix. The admittance matrix is sort of like a graph Laplacian that has the same sparsity of the network itself, the transmission lines. And so why is this a low pass graph filter? Actually, this is exactly what will be an integrator, 1 over s to the minus 1. And the only reason why this matrix is not singular is because there is some leak of energy out of due to thermal losses. And so this diagonal element makes this very ill-conditioned, but still invertible. Now, there is a caveat here. These are complex signals, and so you have to define graph signal processing of complex signal. And my student and I spent some time doing that. So I won't bore you with the details, but the only detail that you need to know is that if I have complex eigenvalues, because this is a symmetric but not Hermitian matrix, how am I going to define graph frequencies? We found we can utilize, if there are no repeated eigenvalues, which empirically, typically there are not, the absolute values, right? And so here I'm showing to you the GFT of voltage phasors for a big synthetic case that's produced realistic state values. And you can see that as this kind of 1 over f behavior because of the inverse, right? So it's the low pass filter is 1 over s. And this low pass property, interesting. So this has a property. So if you have an integrator, then if you decimate the graph signal, you also get a graph signal. So this is just a proof where you actually, what you have to use is a GSO, which is the Cron-reduced matrix obtained from the Laplacian, the original GSO, essentially taking only the reduction is taking the subset of nodes that you are selecting. And these low pass graph properties are maintained. Here, though, the excitation comes again from this Cron reduction. So it's not the original S, it's a different S, which is itself a function of the original excitation. So I don't have a lot of time, so I want to go through a few properties. We already talked about the fact that the covariance is going to have low rank as a result of this being a graph signal that is in general with a sparse spectrum. So this essentially goes directly to a sampling result. How do we sample the signal where we need an anti-aliasing operator, right? And this, in this case, would be projecting over these k low pass frequencies. And then we need an operator that is sampling, which we call a vertex limiting operator, is essentially rows of a permutation matrix that is picking the entries. And so the reconstruction formula for sampling is the following, and it comes from the two operations being cascaded. You have a band limiting operator, then a vertex limiting operator, and then you reconstruct the signal. And in this case, an optimum sampling method can be derived if you can maximize the smallest singular vector of this matrix that you are trying to invert. And this is combinatorial, but a greedy search does well. So this is just an example where we decimated a signal which has, again, from the grid, 2,000 buses, and we have a reasonable reconstruction even with 500 measurements. Because you have a Laurent signal, obviously you can also decimate, and because you have missing samples at random, not just using the same pattern. In this case, it's obvious that you will want to apply some kind of matrix completion approach, right? So M is selecting entries at random, and you try to form the reconstruction by matching this. But in this case, what you want, instead of just using nuclear norm, you know that you need smoothness with respect to this operator. So this will be variation of the signal with respect to the spatial aspect, and this variation in the samples. And so you can recover very well the signal.
So I guess one question about that, but the nuclear norm would be like helping enforce low rank.
This is better.
This isn't quite enforcing low rank, or it is sort of is the rank not the right idea here? Is that my question?
It is indirectly, because L is just picking, but L knows the subspace, right?
Right.
While you are doing nuclear norm, you say, I don't know what the subspace is small. Okay, right. So you're using more information that you have about better side information about the signal.
So I guess would that say for matrix completion, if you had side information about the subspace, you could do something smarter than, something better than nuclear norm?
Of course. Yeah. If you have pure information, you just search in that subspace.
Yeah.
If you have some inaccurate information, right? Here you don't have accurate information, but you are encoding in L what's smooth or not smooth, where it should go, right? It should go somewhere in the against the range space, like in the small range space of that. Why in the smallest range space? So you want this to be small, right? Because you want the signal to be.
I totally understand where you're coming. It was just interesting to me because.
I appreciate the point, because that's an important point, right? Why is nuclear norm worse? Precisely because of what we said. You know more here. This is one of the last applications I want to talk about. So a lot of people have been interested in identifying, learning the graph itself, right? I said in many cases, you don't know it. But in this case, the best results are when you have not a low rank excitation. So what can you do if you have a low rank excitation? So I'm going to skip the graph learning formulation, and happy to share the slides with whomever is interested. So in this case, even if you have a low rank excitation, what happens is that you are going to observe a signal which is low rank in general in the lowest eigenvectors of the signal, because that's what the graph filter is going to highlight. And if you don't have a perfect matching between the spectrum of the excitation and this is what you are going to be indirectly observing. And so what you can do is essentially take the principal eigenvector of the covariance matrix as a surrogate for the least significant eigenvectors of the Laplacian matrix. Now, the least significant eigenvector of the Laplacian matrix appear in the famous problem of spectral clustering, where you are trying to minimize what is called the ratio cut, which is essentially the weight of edges that connect different groups. So you're trying to find the partition, essentially, of the network and make sure that what connects this partition is small. This would be the measure. And this is a combinatorial problem, but is a way of rewriting the ratio cut, relaxing the fact that you're searching for a combinatorial solution, which gives essentially the same solution as the least significant eigenvectors of the Laplacian, which are the principal components, as we said, approximately of the covariance matrix. So this is what the ratio cut idea suggests. In order to find a partition, do a K means clustering of the each of the rows of this matrix, because they will tend to have different signs. So since you are estimating indirectly through the covariance, through the principal components of the covariance, this subspace, essentially what we propose is to do exactly the same and to try to recover the communities just from the graph signal without doing any network inference. And we actually were able to obtain some bound on the performance that we will obtain. Again, I don't want to bore you with the results, but this will be a function of the low pass factor eta k. So when eta k is much less than 1, what dominates over this is the observation noise. And obviously you have some dependencies on the number of samples in terms of the estimate of the covariance. And so this works pretty well. We utilize again roll call votes, and we were able to distinguish pretty well the red and blue states. And we also were able to utilize for the financial data this algorithm and just divide these different firms whose stock we observed in sectors. And so the final result is that if you know that you have a low pass graph signal, everything that you do to the signal, you alter it. For instance, you're trying to do a false data injection attack into a power grid measurement system, then that will cause, since it's a sparse support, that will cause high frequency component. So that's exactly what we did in another paper to detect this such attacks. And you can see that if you have a false data injection attack, you have this graph frequency spectrum for the measurements. Instead, the red is what you get in this case. And so there is a simple hypothesis testing problem you can formulate and looking at the energy of the graph signal in the high frequencies and detect. And you can also try to identify the support. So in conclusion, what is that I tried to discuss here? Low pass graph signal have this nice feature space, which has the lowest, the smallest eigenvectors of the Laplacian matrix. Now, the key point of feature extraction is useful in all kinds of other machine learning programs. One of the very prolific fields right now is that of graph neural networks, precisely because they would essentially generalize the notion of convolutional neural network. And they actually remarkably can be used also for image and videos if you replace the image itself with a simplified stick figure type of model, but that's not the only application. They are also used for graph embeddings, as I said, and ultimately also for graph signal analysis, where you have label data and you can essentially train these algorithms. And the idea is precisely that of convolutional neural network. You want to find a better affine mapping that reflects the spatial correlation properties that you know. And with that, I conclude.